Greetings, everyone, for Rob 201. Calculus for the Modern Engineer. Okay, so let's do a quick summary. Whoops, I haven't shared everything over here. Let me get that going. Zoom folks can't see anything. Share sound, share video, advanced. Okay, thank you everyone for being online. Got you set up. So we'll be going back and forth between notes, and I will not be writing a whole lot today. So if you haven't downloaded today's lecture, please go to Canvas, look in the files folder, look at lectures, and download lecture 25. It'll be the most recent one, please. You got it downloaded? Working on it still? Okay. How are we doing online? Do you guys get the lecture downloaded? Let me know, please. Not so much yet? Okay. Well, I guess you're going to have to write a lot if you haven't downloaded anything. It's going to be hard. So with today's information, you can complete project 3 in 2 hours or less. Seriously. Okay, for the last time, please download lecture 25 from Canvas as I posted it on Piazza over the weekend. So we'll get going. So with standard second order transfer function, we can predict its transient response very easily. We parameterize it using two numbers, omega n, the undamped natural frequency, and zeta, the damping ratio. Zeta sets the amount of overshoot. So you can see this gold line here is 5%, and then 10, and then it gets more and more and more. You can go for no overshoot, and then the response tends to be quite slow and sluggish. So usually there's a range of values that'll work for any given application, and we're using, you got it downloaded? You do, great. It should be in lecture notes. You guys ever get the lecture notes?
Also, it's on Piazza.
Yeah, it's also, you can click on Piazza. Rob 298, go to, whoops, I gotta log in again. Go to Files, Lecture Notes, Select date modified, should come to the top, or date created. Yep, and it's right here at the top.
Okay, they're all saying the file folder is like completely empty somehow.
I just got it open right here.
Yeah, I'm not 100% sure what's happening. I can email the class the file maybe because I didn't pull them. I'm not sure why the files aren't showing up.
You serious?
Yeah, I'm getting them. Yeah.
There's nothing in the files folder? That is a travesty. Okay, online, you guys were able to get it? Just say yes or no. All the files seem to be deleted for me. Everybody else has that too. Wonderful. Okay.
On my end, I'll see if I can just re-upload. Yeah.
Okay, you guys may have to jump on, where else can I put it? Let me do an announcement and attach it to that. Oh, come on.
I downloaded the PDF. I'm going to see if I can make it the outside announcement.
Yeah, I'm just made a, so you should have an email from me with today's lecture attached. Okay, everyone, look in your email or go to announcements on Canvas and you'll have today's lecture there. Shouldn't be that hard. Shouldn't all disappear. Okay, did you get it? Okay, on your mark, get set, go. We're only 9 minutes late, okay? So that's okay, we're going to finish early and we still will. Okay, so everybody sees the standard second order transfer function. The idea is you can write some notes on this if you need to. Otherwise, come back to it and you've got a blueprint to finish project 3. Because I know some of you haven't started the practice final and you need to get going on that too. So it is like it is. So the damping ratio sets the overshoot, and with the undamped natural frequency, you can set the 5% settling time, which is how long it takes to get within 5% of the steady state value and stay there. So fast settling times usually mean fast response. And so you can use complete formulas for it, but the for the overshoot, but we usually use these simple approximations. You can see they're very good. 10% versus 9.5, 5% versus 4.6. For engineering, you can't tell the difference. Okay, so we started looking at PD control to take a nominal plant that maybe doesn't have the right overshoot or doesn't have the right time of response, or maybe is even unstable, and then try to make it stable. So this becomes the forward path transfer function. Then we do G over 1 plus G and clear the denominators to get the transfer function from the reference command to the output. And this is what you get. You get a second order transfer function, and I've tried to make the coefficients from the PD controller show up in the clearest way possible. And so, if you would like to make the closed loop system a standard second order system, at least in the denominator, then you need to identify the very last coefficient as omega n squared. The middle one here is 2 zeta omega n. And then it's just a simple algebra. Once you have settled on the undamped natural frequency and the damping ratio, to solve for Kp and solve for Kd. Now, something we noticed is that the PD controller, it has a numerator, which means it introduces a 0 into the plant. So even if our plant, and this is looking like the balance part of the segue that we will get to, it only has a constant term in the numerator, and us, in order to stabilize the plant, because it's actually unstable, we introduce this PD controller, and so we get really beautiful response, except it doesn't match our expectations. And the reason for that is the 0 in the numerator, the s acts as a derivative. S equals d by dt. 1 over s is an integral. S is d by dt. So when the reference command goes through the plant, it gets differentiated, and that adds to the overshoot. So what we can do is insert a precompensator before the actual reference. And here, the precompensator is set up, so it's got z over z, so when you set s equals 1, the gain here, this just becomes z over z, which is 1. So this coefficient kf is the gain of the transfer function, and we'll use it in just a second. But the z over s plus z, we use the s plus z as a stable pole to cancel a stable 0. And then we're back to something that has almost exactly the second order, standard second order system. So once again, this is omega n squared, 2 zeta omega ns. And this is the transfer function from the reference to the output of our closed loop system. Questions on that? It's something we wouldn't think to do just by manipulating differential equations, okay? You wouldn't think to do that. But this is where the frequency domain or the Laplace domain gives us new ideas. Okay, so if that 0 can be canceled in a stable way, which means the 0 has to be over here in the left half plane. So this is where poles have negative real parts, whereas on this side they would have positive real parts and cause explosion. So if the 0's on the good side of the imaginary axis, we can set a pole approximately, or mathematically, even exactly, on top of that 0, and then it will disappear in from the response from the command to the output. Now, if you take Geeks 460, you'll see that there's maybe some other small issues, but for us, this works quite well. Now, the next thing is, here's the output, here's the reference. We would like it to be such that if we set the reference at a constant value, the output goes to the same constant value. So that's the first thing I want to go through today. It's called the steady state response of the system. So if we have a transfer function, and then we have y of s equals g of s times an input, and then we choose that input to be a unit step, this is what we are faced with. Okay? Now, it turns out you don't have to do the entire inverse Laplace transform to compute the steady state value of y. And the reason for that is, well, suppose G has a bunch of poles here. If they're distinct, then we can do a partial fraction expansion. We've got a pole here from the 1 over s. So we include that in the partial fraction expansion. And then these are the terms that come from the transfer function itself. Now, if the poles have negative real parts, then all of this, when we go into the time domain, we get terms that look exactly like this. So if the real part of P is negative, then that just goes to 0. We don't care about the oscillations. They will be crushed by the decaying exponential. So the only thing that will survive if the transfer function is bibostable is the term that comes from the unit step. And we can calculate that coefficient with a limit. So for these terms, we'd multiply by s minus pj and take the limit. Well, for this term, we multiply by s minus nothing, just by s. And then here's y, this and this cancel. And so we're just left with the DC gain of the transfer function. Okay? S is a frequency. When we set it equal to 0, direct current. That's the electrical engineering term for it. Well, why is that interesting? Well, here, I took all the coefficients outside. These terms are setting the poles of the transfer function, but we've got one parameter left that we can tune. And so if we set this product equal to 1, this product divided by this number equal to 1, then the DC gain of this transfer function will be 1 as well. So this will vanish, we have this divided by this, and we just use that to solve for KF. And then that will have it such that if we command 1 meter per second here, we get 1 meter per second here, whereas if the DC gain is 0.8, we command a meter per second here and we get 0.8 here, or if it's 3, a meter per second, and we get 3 meter per second here. So if this is going to be a command, a reference for us, it's nice to use that freedom. Okay, so that's just algebra. Okay, so you can just solve for the gain, KF, in the precompensator to make this truly a friendly system for us. Okay, so this will be omega n squared. You're going to set this equal to omega n squared, and then everything is going to be such that we have a standard second order system and everything looks like we expect it to from here. Okay, so choose KP and KD for overshoot and settling time. You'll get close to what you want, except the PD controller kind of bites you back a little bit. Yes, I'm making the system stable, but I differentiate everything that comes through my path. And so you can fix that with a pre-compensator. Okay, so let's get this out of the way. Probably the last one for the term. Going to be exciting, Max, rebuilding Canvas if all the files are really gone. I've got them all. Something's up. Going to be fun. We're good? Okay. So what I thought we'd start with, before we get into the nitty-gritty, is a little bit more intuition on how PD controllers work. And so one of the intuitions I want to give you is that a PD controller is allowing you to look into the future. So we're going to look at two videos. One is controlling self-driving cars, and the other one, a wise driver talking to an inexperienced driver. Okay, so if we have just a proportional feedback, the input to the plant is just a proportional gain times the error signal. Okay? Now, imagine that you are driving a car. There's a line in the road that you're supposed to follow. We know on real roads there's lines you stay in between, but imagine that there's an additional line to help novice drivers to keep them in the center of the road, and that's the one that you are using. Now cut a hole in your floorboard and look straight down through that. If you see that line in your hole exactly, then you're right on the path and the error is 0. If that line is to the right, you have to steer to the right to bring it back to the middle. And if it's to the left, you have to steer to the left to bring it back, okay? So, how successful are you going to be? You're not looking out the front windshield, you're just looking literally between your knees through a hole in the floor. So that's what proportional feedback is doing. You're only getting instantaneous error. Instantaneous. I only see the error at this time. That's why I insisted you put a hole in the floorboard of your car. Okay. Okay, so let's just watch this video.
The technology being developed for driverless vehicles is pretty incredible. In the near future, there will be robotic cars traveling on normal roads with the safety and efficiency of the best human drivers. These autonomous vehicles use various sensors to be able to localize themselves in any environment.
Okay, so this was several years ago, and
detailed plan to get from their current location to any desired
you guys know all the hype,
This
but
video
you've
will provide
seen
an introduction
Waymo.
to how these autonomous vehicles are then able to follow their desired trajectories. Getting a vehicle to follow a trajectory may seem simple to those who have driven before, but is it? Let's take a deeper
Yep,
look
driving
at
is
this
so
in a lab
easy, our
setting.
dogs
If
can
we
do
want
it,
to follow a
right?
line, but we are too far to the left, we turn to the right, and vice versa. But how much do we turn? If the steering wheel is turned a fixed amount to the left or to the right, the approach is called bend. But is it?
Okay, so just pointing out, if you're to the wrong side, you steer back to the line. But if all you know is how far you're away from the line and you're acting proportionally, you have no idea if you're currently driving towards the line or driving away from the line. You just know your distance from the line. That's what he was trying to say.
Setting. If we want to follow a line, but we are too far to the left, we turn to the right, and vice versa. But how much do we turn? If the steering wheel is turned a fixed amount to the left or to the right, the approach is called bang-bang control. For controlling a car, this doesn't actually work that well. The response is very jerky and uncomfortable for the passengers. Fortunately, we don't have to steer like this in a car, since there is a range of angles the steering wheel can take. One way to set the steering wheel angle is to use what is called proportional control. Rather than turn the wheel a fixed amount, proportional control steers harder the further away we are from the desired trajectory. We take a measurement called the cross-track error to define how far away from the desired trajectory the vehicle is. Therefore, the steering angle
we're going
we
to
use
make
is
a
this
correction
cross-track
that's
error
proportional
multiplied
to
by a
the
scaling factor
size
called
of the
proportional
error.
gain. The range of values the proportional gain can take drastically alters the performance of the vehicle. As you can see from this overlay, the performance gets better as the gain increases.
And that's how most of us would look if we're just driving by looking through our floorboard. You agree? You get over here, then you overcorrect, and you correct, and you're just constantly oscillating. Forget about bang-bang control for now. We're not using it.
The result of this is that the controller will repeatedly overshoot the actual desired trajectory and not actually follow it. To correct this overshooting problem, we need to consider additional error measurements and use them to update our steering wheel.
P plus
a good candidate for an extra measurement is to look at the
cross-track rate.
Or in other words,
and rate
how fast we
means
are moving in a
derivative.
perpendicular direction with respect to the desired trajectory.
Okay.
If we are perfectly following the trajectory, our cross-track error rate will be 0. In control theory, this is what is called a derivative term. This rate term can then be multiplied by its own gain and added to the proportional term to construct an updated controller. Now that we have two terms, we have two gains that must be tuned simultaneously. Conceptually, we can think that increasing the proportional gain will increase the pull that the vehicle feels towards the desired trajectory. Increasing the derivative gain increases the resistance the car will feel against moving too quickly towards the line. Fixing the proportional gain, if the derivative gain is too low, the system will be what is called underdamped and it will still oscillate. If the derivative gain is too high, the system will be what is called overdamped and will take a long time to correct for offsets. Properly choosing the derivative gain
really
allows
big.
the car to approach the desired trajectory quickly with a cross-track error
And if you
rate
get it
close
just
to 0.
right.
This is called being critically damped.
Yeah.
Despite the
So that would be
success so
zeta
far,
equals
for a complete
1.
controller, we're not done yet. Environmental factors or mechanical defects can change the vehicle's
Okay.
nominal behavior.
So, now, in our mind, in theory, we could be trying to predict a derivative from a line, but humans, we don't do that. We do this. We have a front steering wheel, and then I'm going to relate that back to PD control.
Or they're looking at the asphalt instead of looking at the turn itself.
So
Here's
this
an
is
example of what most beginners see when
rookie
turning.
driver
They see
or
the house
looking
in
through
front,
your feet.
the sidewalk,
You just
the
see
asphalt
what's in
right
front
in front
of
of
you,
the car.
nothing
Now
else.
here's what a more experienced driver sees. They look into the curve itself, they know how sharp the curve is, if any of those people is going to start crossing the street, and so on. Basically, they're looking far into the turn. Of course, you have to scan well in front before you look there. But when you've determined that everything is safe, look far into the turn. And don't look at the asphalt too close to the car either. Lift your eyes and look at the horizon.
So the point here is that you guys remember when you first learned at 16 or 15 how to drive and you were looking basically at the hood of the car and you're making very quick corrections, and then your teacher, whether that was a guardian or a course at school or something, said, look ahead, relax, breathe, okay? So what they're trying to do is to get you to look ahead and plan ahead, okay? So how does that relate to PD control, the fact that you can look ahead? Well, we know how to expand a function about a given point. So the error at some future time is the error at the current time, and we don't really need those zeros there, times the amount of time that we are looking ahead. It allows us to make a prediction of what the error is going to be in the future. So derivatives allow you to predict ahead, which is looking into the future. Now here's a PD controller. You get Kp times E plus Kd times E dot. And so what am I showing it here is that we've got the error plus a term times the derivative. That's this term right here, okay? So when we set the ratio, Kd over Kp, which is 1 over something we'll be looking at shortly, it's how far we are looking ahead into the future. So that's why PD control can help you arrive at a desired value in a much smoother way than just using proportional control. It's making predictions, just like we do when we're walking in the atrium and we see somebody walking out of a classroom. We make a prediction. We make a prediction of whether they're going to hit us or not, and then we alter our path or slow down or something, okay? So this is from linearizing the error, okay, and then looking ahead a certain amount of time. That's what PD control is doing. So that's another way to look at it. So I don't know. Helpful, not helpful? In some sense, the algebra here, this positive and this positive makes it bistable. And then choosing damping ratio and undamped natural frequency for overshoot and settling time, maybe that's all you need for your intuition. But this is another way to think about PD control and how you are using it all the time, because you know where you are and you know where you want to go, so you're able to make a plan and take that into account more smoothly. Questions, comments? Helpful, not helpful? Helpful, boring, don't use it next semester, get rid of it. Okay. Neutral. Come on, online, let us know. Okay, equilibrium points. We talked about this very, very briefly at the end. Let's review it. If we have a differential equation, an equilibrium point is when the right-hand side is 0. And if x dot is 0, x is staying constant. So it's in equilibrium. So that's how you define an equilibrium point. And so if you want to find the equilibrium point for the pendulum, okay, so this is f of x. We set f of x equals 0, 0, because it's a two-dimensional vector. So that gives theta dot, which is what x2 is, has to be equal to 0, which makes sense. At an equilibrium, the pendulum should not be moving, so its angular velocity should be 0. And then the next thing that has to happen is sine of x1 has to be 0. Now that can happen when the pendulum is straight up, which depending upon your coordinates is 0 or pi, and it can happen when the pendulum is straight down. Okay, so there are two equilibria. But you just set sine equal to 0. Yes, there's an infinite number of multiples of pi, but we only need 2 of them physically, one up and one down. You want to use minus pi for down instead of pi, more power to you. Okay, so that gives you the 2 equilibria. Now, one thing we know with a nonlinear function is we know how to do a linear approximation of the function around a given point. And for differential equations, it's interesting to replace the nonlinear dynamics with a linear approximation. And I'll write that x is small, where delta x is the deviation from the equilibrium point. Okay, so we know how to do that. We take f evaluated at the equilibrium point plus the Jacobian at the equilibrium point times delta x. That's how we do a first order approximation of a function. The pendulum, it has two equilibria, so we can do two different linear approximations, one when it's up and one when it's down. You'll get two different matrices. With this one, you'll get one eigenvalue that's positive and one that's negative, and the positive one will cause it to explode away. And downward, you'll get plus minus I for the eigenvalues. You can compute those, and that's oscillation, which is what you expect from a pendulum. Okay, now for the robot equations, which is what the segue is. Okay, so here's our f of x, where x, that's in Rn. We have n variables, and this is also in Rn, so we've got lots of variables, but it's still f of x, and we set this equal to 0. So the velocity, the generalized velocity, so this is q dot. X, that's the generalized positions, q. So the velocities have to be 0 at an equilibrium. Surprise, surprise, okay? Not. Now, just like with the pendulum, then we have to go to the second row. This is a block. It's really n rows, but still, it's a block. We already know x2 is 0, so this does not contribute anything. And we've got d, the mass inertia matrix, times the gravity term. This thing is invertible, so d inverse times g is 0 if and only if g is 0. And so that's the condition for an equilibrium point. For the segue, you would have a couple of equilibrium points. The base can be up, or it could be in a crashed position. Here's another equilibrium. Now, it's a little bit strange in that because the wheel is symmetric, the wheel can be at any position and we still have an equilibrium. So they don't have to be distinct. There can be a continuum of equilibria. So it's usually only when there's a totally symmetric element in the system. And that doesn't happen unless you've got wheels mostly, or gears on a motor. Now, solving this equation, we would normally use NL solve to find the various roots. On the segue, our intuition is enough to solve it. Straight up, okay, and then we might as well put the wheel at some nominal position because we'll have an encoder that's measuring this, whereas this one is an inertial measurement unit. So if we were doing the model as x dot equals f of x, there's the Jacobian linearization, and you get a different a for each equilibrium point. It depends on the equilibrium point. And so the pendulum, it's super easy. Here's the first row in the Jacobian. We would take derivative with respect to x1, that's 0. Derivative with respect to x2, that's 1. Then we take the derivative with respect to x1 and we get a cosine evaluated at, say, 0 for one of the equilibriums, and then this is the coefficient that shows up. And then we take the partial derivative with respect to x2. There is no x2, so it's 0. When we have the other equilibrium, so when the pendulum is straight up, for example, if that's the way it is, then cosine at pi becomes -1, and so the sign flips between the two equilibria. Okay, so you get different models for different equilibria in general. Okay, so that's got all the calculations there for you. Now with the robot equations, it would be really painful to calculate the Jacobians the way we just did when it's already written as a first order term. So here we've got the robot equations. This is second order. Okay. You can linearize the model in this form, and it's also pretty simple. You get the mass inertia matrix evaluated at the equilibrium point. Delta Q is just Q minus Q equilibrium. So delta Q dot is just Q dot, okay? So those become the states of the linear approximation. Delta Q double dot, that's just Q double dot because QE is a constant, okay? So this is the model. Mass inertia matrix at a point, you have to calculate one Jacobian. It's of the gravitational terms, and that's it. So there's the linearized model in second order form. And then you just define x1 equals delta Q, x2 equals delta Q dot. Not x2 dot, it's x2 equals delta Q dot. And then you build the linear model, and this is what you get. So it looks just like the pendulum model. It's got a 0, it's got a 1, except it's a whole matrix of 1s. It's got something in the lower left corner, and then it's got 0 in the lower right corner. Now here we're including torque terms, and you just have to take my word for it that this is how they enter into the model. So if you have the robot equations with torque terms on the right-hand side, do D inverse times everything, and that's where that shows up here. And then we need to take the G on the other side and just isolate the Q double dot. Okay, and when you do that and you choose x1 as delta Q and x2, or I guess here I'm writing it as delta x1, delta x2, you get a linear model written in first order, so we can simulate it easily using the standard packages in Julia. Okay, so that's how we go from a nonlinear model to a linear approximation. And once we have linear models, we can compute transfer functions. Okay, so in project 3, the early part of the project, you compute the Lagrangian for a simplified version of the segue, point masses and things like that to get the robot equations. And then you're given all the tools that makes it very easy to form the linearized model. So that's what you're doing in the first part of project 3. No control theory, okay? It's stuff from chapter 6. And the only thing new is linearizing the nonlinear model to get a linear differential equation. Okay, so the next part of project 3 is to make this segue where it's writable. Okay. And if you want to see one of my robots riding a segue, you can do that on YouTube. Okay, so here's the coordinate system we're going to use. one big bad segue. Okay, so the lean angle is theta, and then how much the wheel rotates, that's called phi. So there's an encoder here. The encoder is mounted to the motor that is mounted to the base of the Segway, so it can measure through gearing potentially the rotations. That encoder will have a 0 someplace, and so we'll just take that as our nominal equilibrium point. So now, I want to convince you of one physical thing. So if this is the origin, and so x is measuring where we are, x is equal to the radius of the wheel times the absolute rotation angle of the wheel. Theta, absolute angle of the base, the Segway itself. Phi is the relative rotation of the wheel with respect to the base. So, question. If the wheel doesn't rotate, can I move sideways? No, no. How about online? If the wheel does not rotate, can I move the base sideways? Online, you gotta answer. Okay, I'm taking you guys all as the wrong answer, and I won't tell you what that is. No sliding. No sliding. I'm not cheating. Okay? No. So, it's lined up. We're going to see what the encoder measures, okay? So, everybody see where is that approximately marking the position, maybe here? Is that a good mark for where the axle is? I'm not going to rotate the wheel. I'm going to rotate just the top of the Segway. Is this and this in the same position? No. So if x is the distance from the axle, from where it moved, it's the absolute angle of the wheel. Here, I'll show it slightly differently. Okay, we'll put the wheel is straight up, so you can see that here. Okay, so the wheel rotated in the absolute coordinate frame. The encoder registers nothing because it didn't rotate like this. Okay? So that's just physics. That's just physics. So the x translation, and we're going to use the axle as the center of the Segway. Makes sense, right? And so that is related to the absolute rotation angle of the wheel, which is theta plus phi. And so when I held theta 0, the relative angle, and I changed phi, you saw that x moved, okay? So it really is the sum. Everybody convinced? You're going to take away your nose now, and you're going to say, yes, the Segway can move without the encoder registering anything. See, I asked the question in a tricky way, without the wheel moving. The wheel moved in the absolute, but the encoder said it did nothing. Okay, so if that's the position, the velocity, when we control the velocity of the Segway, it's x dot, and so it's the radius of the wheel times theta dot plus phi dot. And so you will calculate the two transfer functions for the Segway. So what we're going to do in the remaining time is calculate controllers for it. We want to control two things. We want to keep the darn thing upright because we don't like falling off it, and we'd like to be able to regulate its speed. Now, as a human riding this thing, or you're riding a hoverboard, it's the same principle. It's the position of the center of mass of this that controls the speed. When you do the BallBot and Rob 311, you are not riding it, and you need a secondary controller to do what the human body would do. Okay? Just like all of you probably one time or another have ridden a bike, but you know if you just take the bike and push it without you on it, it doesn't stay up, it needs a controller. You are doing feedback control to keep the bike up, and you're doing feedback control to adjust its speed. If you've ridden a Segway, you know that by leaning forward, you can accelerate, and leaning back, you decelerate or brake. So the two transfer functions are as given here that you'll have to work with. It'll be slightly different for the BallBot, but they have the same structure. Now here's why it's hard. We have one motor. Well, because we're doing a planar model, there's really one motor for each wheel, but we're going to have the motors moving in sync. So we're just moving in the plane. So we have one actuator, the torque on the motors, and yet we want to control two things: lean angle and speed. That's hard, okay? One actuator, two objectives. If you have one actuator per objective, it's much easier. So this is called an under-actuated system. We have two control objectives, but we do not have two independent control signals. We just have one. Now, there's a feature, and this is where physics comes in, okay, and the math supports it. When you look at the transfer function from torque to speed, do you see anything in common between the transfer function from torque to lean angle? What do you see in common? Well, there's an S, okay? I give you that, okay? But more importantly, you see this term? It's replicated here. Now, gain, that's easy. You put 4 here, you multiply by 4 here, you divide by 4 here, it's all the same. What we're going to take advantage of is that this transfer function can be written as this one times this numerator term, this denominator term, and then, I don't know, what does it take to go from 21 to 20? You multiply by 0.95? Okay, so that's the constant, okay? So this transfer function is essentially 0.95 times s squared over that divided by s times this one. And so you can think about it as being here, and we're going to take advantage of that structure. But when you have a difficult control problem, you always want to focus on the essential first. And what's more important? That this thing is upright, or that you've got the speed exactly where you want it? Well, I don't care how good the speed is. If it's like this, it's not good, okay? This is more important. Now, if you're going fast and you fall off, I agree there's some issues there, but still, in the whole scale of things, keeping this thing upright allows you to then potentially start thinking about regulating the speed. So the first thing we're going to focus on is regulating is balancing the Segway. So here's the transfer function from torque to lean angle. We're going to use the one tool that we've learned in this course for control, a PD controller and then we'll fix up the zero that's being added and the DC gain with a pre-compensator, okay? So we're gonna take a break and then we're gonna take some extra time. So go through the motion of computing KP and KD for this transfer function so that the closed loop system has a 5% overshoot, so choose your damping ratio, and then the settling time is 270 milliseconds. And then if you get all that done and you have time, you can adjust the gain here such that the gain from theta desired to theta is 1. So you command a lean angle and you get it, okay? So it's break time. Any questions from the online group? So there's a workflow. Set your performance specifications, and for us, percent overshoot and settling time. In the project, you're going to use zeta as 0.7, and I'll give you a settling time, okay? You're not experienced enough to be choosing these, okay? So just give it to you. And then once you know the settling time, you just solve for the undamped natural frequency. Once you know those, then you know omega n squared. This is known, that's the model. You're trying to find these guys, and now it's algebra to solve for this so that the overall thing is your undamped natural frequency squared. And then you solve for this one such that 2 zeta omega n. So that's the workflow. Still have a minute or two if you want to keep doing your calculations. Okay. We'll do this. Okay. In case you've forgotten how to get to this, you go to Pages, Code from the textbook, pick the chapter, and then, you only have student view, but then you want the part with the demos. So that's what we're doing here, the demos. Pages, pick the chapter. You've got access to all this code that's in the book. So if you copy and paste it from the PDF, it'll mess up all the F's and several other the letters. Okay, so here's the transfer function for speed. And we write it as a constant over s squared plus a1s plus a0. So it looks just like what we had a second ago as the canonical second order system. We choose a PD controller, so now we know what goes in here in the compensator. Just as we did before, we calculate then the closed loop. And so here's the G over 1 plus G. So it's G theta times the compensator in the forward path. So P of S here is the angle, balancing angle transfer function. And then we have the compensator. And all I've done here is grouped all of the terms that have an S and all of the terms that are just a constant and put those over here. Come on. Okay. Okay, do not do this to me. Do not. Oh my gosh. Good. That happens to you guys all the time too, right? So it's only fair that it happens to me. Okay, so let's go back. I think none of the cells, oh, maybe some of them are run still. No, I don't think so. Okay. So PD control of a second order thing. Here's the plant. Compensator. We want to tune the parameters so we get a 5% overshoot and a 5% settling time is given to us. No, that's not the segue, is it? If it's demo 4, it's correct. Okay. No, we want demo 5. I knew it wasn't right. There we go. Here's the segue. That's getting the model. Skipping all the transfer functions. You guys will have no trouble with that. Sorry, I had this all set up. Okay, here's where we were. Here's where we were. And probably I have to rerun the cell. Right? Yeah, I get to run the cell. Okay, so then we calculate Kp and Kd. And so you can just have these formula, well, you don't need them on the final exam, but you can just use these formulas when you do project 3. Okay, so we get the undamped natural frequency. The settling time is 270 milliseconds. From that, we calculate the undamped natural frequency. We were given the damping ratio, and now we get the proportional and derivative gains of the controller. And then we do the step response. And it's close to what we want, but it's not what we want. So we put in a unit step. It's settled out at 1.2, and the overshoot here is more like 20, it's 15%. Okay, I calculated it. So we fix that with a precompensator. This has a 0, s plus z. We put 1 over s plus z here, and then we're going to adjust all the gains such that the DC gain from the reference to the lean angle is 1. Okay. Okay, so now here's the step response for the lean angle. It has very little overshoot, and if you want even less, you could make the damping ratio equal to 1, and then it will have no overshoot. It'll just come up and then settle in. What we're looking at here is the torque, because eventually what is making this thing stand up? It's the motor, and this is just showing it looks quite similar to this. So there's nothing, no crazy oscillations in the motor torque. We got lucky. Okay. So it's sad that I have to move these things around, that our connectors aren't good enough. Okay, so in the code, you can find all the calculations for getting the terms in the PD controller. So this is KD pulled out. This is KP over KD. There's the transfer function. This is written as S plus Z, Z over S plus Z, and then calculate whatever gain is needed here such that the gain from theta desired to theta is 1. Okay? So that's the kind of the third part of project 3. First part, Lagrangian model. Second part, form the linearization and get the transfer functions. So you'll have this part and you'll have this part. Okay, so now we're going to take advantage of the fact that this model has special structure. So this comes from the physics, not from calculus. This comes from physics. This is not calculus. Calculus is computing Laplace transforms, transfer functions, etc. Feedback control is analyzing G over 1 plus G, and then understanding when you can take one compensator, multiply times another, and do a deliberate pole zero cancellation. Only when you have a stable pole. The pole here is minus 13 in the left half plane. So now, we know how to adjust the torque. There's the torque to control the angle. Okay? Here. This is where the physics comes in. So I can take this and add it right here. Or I can take all of this and add it here. It's up to you. So here's my measurement of the angle with an IMU. And then this is my speed. Okay, so that's all I've done. We designed this first. And I asked the question, have we pre-pended a controller to this, or did we post-pend the transfer function for speed? It's 6 of one, half a dozen of the other. But this is our transfer function now. This part will allow us to set this angle at any value we want. 2 degrees, 3 degrees, 10 degrees, 45 degrees? That sounds frightening, okay? That controller will allow us to do it, and it'll get us there with just a tiny bit of overshoot, and the settling time is 270 milliseconds, so it's fast. So here's the thing. We can use the lean angle to control velocity, is what this is telling us. And we have a controller that goes from theta desired to lean angle. So now we're going to use this as a pseudo actuator to control speed. So that's physics. So here's my segue. The amount the body is leaning sets the acceleration. The only thing that can stop this from toppling, because gravity is acting at the center of mass and trying to pull it down. The only thing that can keep it up is if there's another force on it pushing this way. And that force comes from the wheels spinning. That's where your motor acts. So if the wheels do this, we get upright. When this thing is completely upright, there are no forces acting on it, so there's no acceleration on the base, and we're moving at a constant speed. To brake, we need to lean backwards so that gravity, and then we're going to move the wheels in the other direction to come back underneath, and that's how we slow down. To speed up, we lean. So look at this. If I can control the lean angle, I can control the acceleration and ultimately the speed. So that's the physics, and it's the same physics on the ball bot for the Rob 311. Do you have questions on this? Because without this intuition, the whole project kind of doesn't make any sense, okay? You control the hardest thing first, keep the stupid thing upright, and then now you can regulate this. So a human would just use their body, like on a bicycle, to hold this, and that's a constant speed. And then if you're doing your hoverboard or the Segway, you lean it back, and that slows you down. You're moving at a constant speed, you slow down. You want to accelerate in this direction, and then you don't want to accelerate anymore, and now you just keep moving at a constant speed. That's the physics. These transfer functions are telling you the same thing, but unless you're kind of used to looking for that in the physics, you don't see it. So this is what this is the transfer function from torque to speed, factored nicely, and it's telling you that the lean angle controls the velocity. And I tried to show it to you physically. So we are now capable of setting theta to any value we want. So we can accelerate by putting theta forward, and we can decelerate by making theta negative. Okay? So now we're going to write another feedback loop around this. So pay attention, because this looks super frightening, etc. but it's not. So what I'm doing here first is I'm getting the transfer function from theta desired to here. Now, here's the key point. This transfer function we designed to be one of those beautiful second-order transfer functions. To here, this looks like omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Why does it look like that? Because we deliberately designed for that, okay? We set those two parameters to get overshoot and settling time. It introduced a PD controller, which has a 0. We wisely canceled that 0, and then we adjusted the DC gain such that it became 1. S equals 0, omega n squared over omega n squared. DC gain is 1. So this transfer function looks very complicated, but it's this block, and this loop can be replaced by this. So theta of S over theta desired is omega n squared over 2 zeta omega n s. And so the transfer function from theta desired to V of S, you simply multiply by the transfer function that goes from theta of S to V of S. And we put it here. Now, I'm doing another thing that we kind of know how to do. This second order term, we can factor that. It has a 0 at plus 2.722 and another 0 at minus 2.722. What do zeros do to us? They increase the overshoot. So if we can attenuate that effect, we like to do it. Okay. So remember how we did it before. We put a term in front that was z over s plus z. So our s plus z is s plus 2.72. So this is, say, z2 over s plus z2. We're going to add that term in front of here to cancel this 0. Then we're going to give ourselves a gain, and then we're going to just make a feedback loop, just like we've done before. Now, in between, it looks a lot more complicated, but once we cancel this with this, we've got a second order system, we've got a pole at the origin, and we've got 1 0 left. But it's not as bad as it looks. So there's the controller for regulating speed. We're going to use proportional feedback, and then we're going to cancel one of the zeros that's in the forward path from theta to velocity. Okay, it's fairly sophisticated, but it's the same thing we did when we regulated the angle. The PD controller introduced a 0, we canceled it. Here, the natural dynamics has 1 0 in the right half plane, this one, that's unstable 0, and it has a stable 0, and we're going to cancel the stable 0 with a stable pole. And now we have 1 gain left to tune. And when you only have 1 constant to tune, it is totally okay to just put a step input in here for desired speed, look at V of S, and adjust K2. When there's only one parameter, humans are good at making it bigger and smaller. When there are two and you have to move in a grid, you screw up if you have a biological brain. If you take EECS 460, you learn about lots of methods. Now, in the new version of the textbook I put up, I compute analytically the range of gains for bibo stability. But you don't have to know that. This just helps you understand where to start. And because you guys are beginners, where you would start with this, you say, well, I'm just going to set it equal to 1. But notice it has to be negative for the closed loop to be stable. And it's because of this 0 that's over in the right half plane, which makes the DC gain here negative. And so K2 needs to be negative to make this whole thing a positive. Take EECS 460 for the details. So if on the ball bot, you're adjusting the gain at this point, and it's unstable for everything you do, flip the sign. You got it? Flip the sign. Okay, so let's do demo 6. Okay, so we've got the angle controlled really well. It's a standard second-order transfer function. So the precompensator times the closed loop is omega n squared over s squared plus 2 zeta omega ns plus omega n squared. That's why we get 1 here. This number and this number are equal, and when this is S is 0, that's the DC gain, it's 1. Okay, so now this is the transfer function, so we get to do this. Okay, so this is just controlling the lean angle. So this is what we're doing now. Here's the PD controller for lean angle. There is the precompensator, theta desired to theta. Theta desired to theta is the second order system. So this transfer function is really this. This looks terrifying because it has 2 loops in it. It's called an inner loop, outer loop feedback control. But we can design it simply by viewing it as a standard unity feedback. And I'm giving you the structure of C2 of S that you would learn in EECS 460. And so we're going to cancel the stable 0. We can't do anything about this. This gain is to take the pole at the origin and move it into the left half plane. So this is what we're going to be doing step responses for and just adjusting K2. And you don't have to do any of this, okay, analysis, but it's there if you want it. Okay, so there's the step responses from K equals 0.1 to 0.3. I wrote a loop and just chose a whole bunch of gain values and then did the loop and then plotted them. You can do that, or you can just do the step responses one at a time, okay? Now, the command from velocity, think about you having a robot sitting on top of a basketball. Do you think the robot's going to stay on the basketball with this type of oscillation? And the answer is no. Okay, it's going to fall right off. Now, this blue line down here with the lowest gain, so that's kind of your most conservative response. This next one up, the orange one, looking not too bad, right? It's no overshoot, and so maybe we don't get too wild on the angle, but this is what you would look at as a control engineer, and this is what calculus and differential equations, making it real, we're changing the gain and we get to choose the response we want. Now, because this is a simulation, all of them make the closed loop stable. Look, the oscillations die out. So you can do any of those you want. So I'm going to choose the green one here, I guess. The orange one or the green one of those they're both pretty good. This is getting a little bit gnarly. This looks a little too cautious, but hey. Now what I want to do is the following. Here's the torque that's actually going into the Segway. This is a measurement, an IMU gives me this. And then I need to compute the velocity. I need to differentiate theta to get theta dot, and I need to differentiate phi, the wheel speed. So measuring from the encoder, I need to calculate its velocity multiplied by the angle. Okay, so this is an output, a measurement. Come on. So the measurement, torque, and stuff. So this is the feedback diagram, but I want to remove the model because this is my controller. I set the desired velocity and I compute torque. To do that, I need to measure theta and v. So this is the PD controller. Okay, we are commanding theta desired as regulating the speed. So that's our C2 of S. Here's the precompensator. This is the controller that you would implement on the ball-bot. Now in project 3, once you choose this number, the rest of this is basically done for you. Okay, so I will take your values for the controller, the precompensator, and the second proportional. So this is PD, proportional, and a precompensator. I will take that and turn it into, did this run? No, I don't think I ran that one. Okay, if I run everything, hopefully, don't worry about this, it's be done for you. All of this will be done. Okay. Okay. So this is now the response using the linear system. I command a step of 1 meter per second. So let me ask you this. Why do we initially go negative speed before we go positive speed? It's because of this. I want to move this direction. The only way to do that is to get this to lean forward. So what you do is you move the base backwards. It's called non-minimum phase behavior. But if you ride a Segway, you'll feel it, okay? And it's unsettling when you first start, okay? The base needs to move backwards. Now it's leaning forwards. Now the motors can start spinning like crazy to catch up with it, and that accelerates you forward, okay? That's the physics. So this is not wrong. It has to go backwards. It's physics. And it all comes out of the math, okay? And once again, when you take EECS 460 or ME 461, and I forget the aerospace control number, or ROB 315, which is coming online soon, you'll understand this better. But I step the speed at 1 meter per second, then at -1 meter per second. Okay, we're at constant speed. Now you want to go this way. We need to accelerate the base to get me leaning backwards, and now I can slow down and then start accelerating in this direction. Okay, so that's what's going on. Now here's the terrifying part. That's the speed. Okay, so this is 0.1 radian. So 0.1 radian is how much in degrees? Anybody remember? Do a quick calculation. 3 equals 180. So 3.14 radians. So 3 radians equals 180 degrees. Okay? So 0.1 radians is 6 degrees. 1 radian is 60 degrees. 3 radians is 180. 1 radian is 60 degrees. 0.1 radians is 6 degrees. The ball falls off the basketball at 4 degrees, okay? So what this means is you can't send a step that's big. You can only send one that's about 0.5 meter per second. Okay, at least that's what the linear model says. Now we're going to hook the same controller up to the Lagrangian model. Okay, so dynamic model, planar segue, we can see that. Okay, so this is the ODE for the nonlinear model. And the beauty is, look how well we did. I mean, they're almost identical. You can't tell the difference at first blush. So there's maybe slightly more lean with the nonlinear model, but not much. I mean, they look really great. And it's because I helped us to design a good controller. And then there's the segue, okay? And you'll have a similar animation for the ball bot. So you can see it doing that non-leans to get it going so it can go the other direction, okay? It's the physics. It's not that your controller is messed up. It's the physics. And that's the end of the demo. Okay, so the first part, I think you'll have no trouble with the PD controller and the feed forward. This part, it's structured. So if you go back and look at this, and you're given what the compensator for the speed is going to be, but you have to choose, you have to factor this second part of the transfer function for the velocity. And so this and this are the same. And you can leave it in, it's just that your response is much worse. So you can play with it with just you putting a constant gain and not putting in the term that cancels it. So here, I've canceled those so that what you're staring at is much simpler. And in fact, it's second order, nicely stable, a pole, and then this 0 that causes extra overshoot and undershoot. And that's project 3. You can do it in 2 hours. Cool? Okay. So this is the end of the book. It's a lot. So we've got Wednesday. We can do special topics. Do you have anything in mind that you would like to know more about? I have some ideas, but I don't want to bias you. Anything you'd like to know more about? Yeah.
Maybe some examples of like these controls in like applications.
Control of?
I don't know, just some examples like of the applications of this stuff.
Of more feedback control? Is that what you?
Like how it's used in actual, like some
Okay.
examples of like action products.
Okay, so we could talk about a bipedal robot and doing control for it if you wanted. Okay, so that's one thing.
Real life PID.
Excuse me?
Real life PID example like in real life how actually.
Well, I mean, what you're doing here is pretty close to real life. I mean, Justin's system is almost exactly this, right? Yeah, so it's real close to real life. We could talk about some of that. What I was thinking was more theoretical, like you heard of Fourier series? This is where you can write every periodic function as a sum of sines and cosines. Would you like to understand why that works? It's not hard. And if you do Fourier series, then Fourier transforms, then the Laplace transform becomes, it's falling off a log. I mean, what happened was Joseph Fourier was presenting his work at the National Academy of Sciences in Paris, okay? And he was doing Fourier series, and he was claiming that every continuous function, every piecewise continuous function can be written as a sum of sines and cosines. It would be an infinite sum. And some bright member of the National Academy in the 1800s, okay, goes, there's no way that a square wave can be written because it has jumps in it. It's discontinuous, okay? You can't do it. But Fourier was right. You can, okay? Absolutely, you can. And this guy, one of the guys in there who was watching this take place was Laplace. And Laplace looked at the formulas that Fourier was saying he just needed his function to be absolutely integrable for this coefficients to exist. And he understood that if he introduced an exponential that could cause decay, he could take something that was blowing up, make it decay appropriately, and then he could still define an extended Fourier transform, and that became the Laplace transform. So this Fourier got hosed. He couldn't get his paper published. He eventually published a book on it, and enough people read the book and used the results that it became accepted mathematics. And then Laplace, because he was there, he got a real zinger, okay? He got the Laplace transform, and so we could understand differential equations and stability and stuff like that. Crazy, huh? So, okay, I'll come up with some combination of something borrowed, something blue, okay? We'll make it like a wedding, okay? And put something together. And then Monday, we will go through the practice final. So my suggestion is if you haven't worked the practice final at that time, you don't attend lecture. And then you can watch the recording if you get stuck on it, okay? That's my suggestion. Now, I hope after that suggestion, I still get at least one or two audience members, but maybe not, okay? It's okay. Max and I will walk our way through the practice final. And that way you can refer back to that for solutions. Because I promise you, if you prepare well on the practice final, the real final, you'll finish it in 30 minutes. Okay, so that's my story, and I'm sticking to it. We're later than I wanted because we had issues getting going here, and somehow our Canvas site has no files. That's exciting. I wonder why I can see them and nobody else can. So maybe they've all been turned off and we just need to go in and publish them again. So a burp happened on Canvas, so I'll fix that. Okay, thank you.